Strain is an internal effect of force application in materials. This is manifested in the appearance of deformation. This video showcases two examples of solving strain parameters. Welcome to Mechanics of Deformable Bodies. The first problem consists of a lever with a pin at point B, 200 millimeters from point A. A certain force is applied at the handle, causing the lever to rotate clockwise about the pin, which created a 2.5-degree angle. Our task is to determine the average normal strain in each of the three wires. In the original position, the wires are considered unstretched. Strain is computed as a deformation of the material upon the original length. The original length of each wire is measured and given, but the deformation is still to be computed. With 2.5-degree rotation, the bar creates similar triangles among the three wires, of which the change of position of points A, C, and D are considered as deformation. Using trigonometric functions, we equate the tangent of 2.5 degrees as the deformation of wire AH all over length AB of 200 mm. This is also equated as the deformation of wire CG upon the length of 300 mm. And do the same by equating the deformation of wire DF all over the length of BD, which is 500 millimeters. Now we can compute for the strain in each wire. Starting with wire AH, the deformation is taken as the tangent of 2.5 degrees multiplied by the length of 200 millimeters, giving 8.743 mm. Plug this deformation into the strain formula, making 8.732 all over 200, and that gives 0.0437. The same procedure is true with the next wire CG. Its deformation is computed as 300 times the tangent of 2.5 degrees, resulting to 13.098 mm. The strain in the wire CG is then the deformation of 13.098 divided by the original length of 300 mm. Thus, the strain becomes 0.0437. The strain in the third wire is done similarly, starting with its deformation computed as 500 times tangent of 2.5 degrees, which is equal to 21.8305 millimeters. Use this deformation to compute for the strain, which is 21.8305 all over 300, resulting to 0.0728. The second problem consists of a rod ABC made of steel where steel's modulus of elasticity is 200 gigapascal. The two diameters of the rod each contain different forces: tensile force P of 8 kilonewtons and compressive force Q of 42 kN. We are to look for the deformation of the rod at points A and B. We consider the smaller diameter part AB, which contains the force P when we look for the deformation at point A. With the deformation solved from PL over AE, we place P of 8 kilonewtons, which becomes 8,000 newtons, length L of 0.4 meters or 400 millimeters, all over the cross-sectional area of the bar, pi over 4 times the square of the diameter of 20 mm, and then the material's elastic modulus of 200 gigapascal, taken as 200 times 1000 to make it in megapascal, which is newtons per square millimeter. The deformation of rod AB is 0.0509 millimeter. Looking for the deformation at point B, though, takes a different approach in determining the force. Since point B is at the middle portion of the bar, the net force acting at the point should be considered. Thus, we take the difference of forces Q and P as they are opposite forces. 42 less 8 is 34 kilonewtons. This serves as force P in the deformation equation, PL, all over AE. Now all we needed to do is to plug values. P is 34,000 newtons multiplied by the length of rod BC, which is 500 millimeters. Divide this by the cross-sectional area of the lower rod, pi over 4 times the square of 60 mm. Then this is multiplied by the elasticity modulus of steel. The deformation is then computed as 0.0301 mm, and this deformation shrinks the length of the member as the net force is compression.